Hello everyone, this is Physics 30, Unit 2, Lesson 4. Here we're talking about net electric forces and fields. So welcome back to our Physics 20 vector addition stuff. That's really all that's going on here. Difference being that we're just going to be using the force electric and or the electric field. So let's look at example 1. There's 3 examples in this set. Here we go. We got 3 charges, Q1, Q2, Q3. With a negative, positive, negative. We've got the distances between the centers of those charges, and we need to determine the net electric force on Q3, which is this guy here. So what is the net electric force acting on this one? So let's go ahead and draw the object of interest. I'm going to put it right in the middle. It's green. This is Q3. There we go, Q3. So let's think about what it's going to experience. If I ignore Q1 and just think about Q2, well, Q2 is a positive and Q3 is a negative. So this is going to be an attractive force. So Q3 is going to experience a force as a result of Q2. So I'm going to call this the force electric, let's go 3, 2. Okay, it's the force electric between this charge and this charge with respect to charge 3. Actually, you know what? I'm going to change the color of that just so that it's pretty clear that we're using the force from Q2. So let's color code it. Let's go blue. So the green charge, which is Q3, experiences a force electric as a result of 2. We'll call it 2 to 3. Okay, now we're going to do the red sphere, or the red charge, which is Q1. Again, thinking about it from the perspective of Q3. Well, Q3 and Q1 are both negative, so if we only think about the interaction of Q3 and Q1, that's going to be a repulsive force. So now I'm going to draw this in the opposite direction. It's going to push it, it's going to experience a force away, and that is, I'm going to call that FE 1 to 3. Okay, now, I have not drawn these to scale yet, so I've drawn them equal, but they may or may not be equal, and now I have to go ahead and do my calculations. Of course, I'm dealing with the force electric, so I'm going to be using KQ. Now I need to put Q1 and Q3 all over R, so it's going to be the R between 1 and 3 squared. Okay, so that should be fairly easy to solve. I'm going to plug that into my calculator, making sure that I add these two values together. So let me just write this out. It's going to be K multiplied by Q1, which is 7. I'm not worried about the negative. Make sure you do not put negatives on your charge. Charge is a scalar. The negative sign is just an arbitrary value. So we've got 7 microcoulombs, so that's 10 to the negative 6. Okay, and then I've got 5 times 10 to the negative 6. That's my Q3 all over, and I have to add these two distances together because I need to know the distance center to center. So it's going to be 0.14 meters plus 0.09 meters, and this is all squared. Okay, so we put that into our calculator and we get, for the force electric between 1 and 3, I get a value that is 5.945, lots of values. I'm going to keep those in my calculator, newtons. Okay, and that's obviously to the right. Okay. Now I'm going to go ahead and do the exact same thing, but on the other side, the vector arrow pointing to the left of the page. So this is FE 2 to 3. Oh, I forgot to put my 1 to 3 on there. Okay, so FE 2 to 3, and of course this is going to be K Q2 Q3 over the distance between 2 and 3. Oops, squared. Okay, so what does that look like? Well, that's going to be K, Coulomb's constant. Q2 is 2. microcoulombs, and Q3 is 5 microcoulombs, and that is all over the distance between 2 and 3, which is 9 centimeters, so 0.09 squared. Okay, so that gives me, if you plug that into your calculator, you'll get 11.095 something newtons. Okay, so now we're ready to go ahead and figure out our net force. So let me see if I can squeeze this into the middle. The F net, which is the sum of all forces here. Well, let's have a think here. We're going to have, well, let's just work out this F net. That's really what we're asked to find, F net. So it's going to be, let's put it in as, first of all, a positive. I'll use red just to represent this. We'll say that this direction is positive, this direction is negative, just to be conventional. So I'm going to say this is my positive FE13, okay, plus, let's see if I can add this in here, plus I'm just going to make a bit of space here. We'll just get rid of that for now. Plus my negative, because this is going the other way, negative FE13. Okay, so now I know those values. Essentially what I'm doing is just taking one away from the other. And hopefully you can already see, without doing even the calculation, this force is bigger than this force. So if I was to, even before I do the calculation, if I just make my vector arrows a little bit more to scale, they're about twice. So let's go ahead and just make this one about half the size. Well, hopefully you can see that that means that my net is going to be going this way. My F net is going to be moving, applying a force to the left of the page. And that's certainly what I find. So I find that my F net, when I subtract those away, I get a negative, in other words, going to the left of the page, 5.2 something, and that's in newtons. So negative 5.2 or 5.2 newtons. We could just call it out as left. Okay, so example 2, now we have a two-dimensional field question. So here we have a hypothetical point in space. We're just asked to find out what would the field lines be at this location. So let's just think about that briefly and just qualitatively. Well, my green dot is a positive. Now remember, just by convention, we talk about positives being field lines that go away. So positive field lines come from the positive. Sorry, I'll say that again. Field lines come from a positive and they go to a negative. Okay, well, we know that the green, oh, I think I've cut it off. I'll have to put that in. This should be in part of our example. We should have Q2. Q2 should be given, and it's negative 70 millicoulombs. Okay, negative 70 millicoulombs. So we already know that one. So that's a negative. And negatives, as we know, the field lines for a negative go towards the negative. So that field line is going to go towards, like that. Okay, so let's just think about it qualitatively. If I wanted to think about the field lines coming from that P experiences, well, it's going to feel some of it down, but, so some of it's going to be coming down, but some of it's going to be going this way. So I predict that it's going to be in here somewhere. My qualitative prediction is just that it's going to be somewhere here. Okay, that's what I think. And sure enough, if I go ahead and analyze, I'm going to do a tail to tip method here, just because I have my two components. So I can just put those together. Let's see. I'll do green. So my field line here, this is going to be my E1. I'm going to call that E1. And then tail to tip, I can put E2. There's E2. And so, of course, my resultant is going to be my net electric field. So this is my E net. All right. And so all I need to do now is solve for the resultant of this triangle and the angle. Okay, so let's think about what that might be. Well, E1, it's going to be K Q1 over R1 squared. All right, and that's pretty straightforward. Let's just go ahead and put those values in. We've got K, we've got 50, now we've got millicoulombs, so that's 10 to the negative 3, divided by 18 centimeters, 0.18 squared. And that's going to give me, let me see, 1.3873, something, something, something. Oh, it's quite a big number. Got to put that in scientific notation, times 10 to the 10 newtons per coulomb. Okay, and in red, same idea. This time we're looking at field 2. Field 2 is K Q2 over R2 squared. And of course that's going to be K. Q2 is 70. Again, I'm not worried about the negative because it's a scalar value, charge is a scalar value. And it's milli, so 10 to the negative 3, all over 13 centimeters. So I'm turning that into meters squared. And that gives us a value of 3.7236. Oops, not like that. It's 236. 236 decimal times 10 to the 10 newtons per coulomb. Okay, so now I'm going to do of course I'm going to go a squared plus b squared is equal to c squared, my Pythagorean theorem, and I get c to be, what do I get? Yeah, 3.7236 decimal times 10 to the 10 newtons per coulomb. So that's my magnitude. That's this E, my field net. So let me just change the C to field net. So that's E net. Okay, and if you wanted to, you could actually just get rid of the a squared plus b squared equals c squared, replace them with the actual values. So I would say E1 squared plus E2 squared is equal to E net squared. Okay, that's a bit better, isn't it? All right, last thing to solve is for the angle. Well, I'm going to use my red and my green values, my E2 and my E1. So these are adjacent and opposite. So of course I'm going to be using tan here. So tan theta is equal to opposite over adjacent. So the opposite here is E2 and the adjacent is E1. So solving for theta is ends up being 69.5 something degrees. So I'm going to round that to the significant digits, which would be 2. So I'm going to restate my answer in correct significant digits. I'm going to say 3.7 times 10 to the 10 newtons per coulomb, and then 70 degrees. I'm rounding this up to 70, and I'm going to say that it's going from the south this way, which is east. So it's going to be east of south. Okay, and there we go. All right, this third example, we are given a field strength between the Q and the P. So we know the field strength that's a result of this charge Q acting on the P, or that P can experience, and it's going to be the same for this one. So I'm just going to go ahead and start drawing these in. Ultimately, we're going to try and find the net electric field. Okay, so we're given just one of these field lines, but we need to find the net. So let's just go ahead and draw these in. So I know this field line, and it's going to be going away because it's a positive. So the field lines always go away from positive. So this particular field line is going to be going away in this direction. And then I can say the same for this one. It's going to be exactly the same. These two blue vector arrows here are the 500 newtons per coulomb. Okay, the next bit is to think about the components of these blue vector arrows. So let's go ahead and I'll use red for this one. So this is a vector component of the 500, or the blue arrow. I'm going to call this the field 2, x. Okay, because I'm going to say that this, oh, actually, no, I wanted to call that 1. I'm going to call this is my 1, this is my 2. So this one here is, let's call it x1. Okay, which means this vector here is the x component of 2. Okay, and then if I keep going, this component here is the electric field in the y from 1. And then, of course, this is the electric field in the y for 2. Okay, so now all we need to do is figure out an angle. Okay, so if I can figure out this angle here, I know the hypotenuse. This hypotenuse is the given value. This is the EPQ that I was given in the question. And so if I know the angle, I can now solve for the two components. And hopefully you can see that if I consider the x components of the electric field, if I was to do a net x electric field statement, I would say the net, actually let's do it like this. So I would say the x net, so the electric field in the x direction, well, that's going to be the sum of EX1 and EX2. And hopefully you can see that because these hypotenuse values are the same, and because the shape of this triangle means that the angles are going to be the same, these red vectors are equal and opposite. So in other words, they're going to cancel each other out. So I can make the statement that EX1 is equal to EX2. Okay, so they're going to cancel each other out. I'm not going to need to consider the x component when it comes to the total net, the net electric field. Okay, let's look at the greens. So again, I'm going to make the statement that the net field for the y direction, well, that's going to be EY1 and EY2. This time, however, I am going to have a positive value because both of these green vectors are going upwards. So now I just need to get the angle. How am I going to do that? Well, hopefully you can see that since I have a triangle that has two sides that are 700 and the other side to be, two sides that are 7 centimeters and the other side is 8 centimeters, this means that I must be able to split this triangle straight down the middle, knowing that it's perfectly symmetric across that yellow line. And so I can call that yellow line a right angle, which means I can divide this by 2. This means I have a triangle that I can analyze using the dimensions to get the angle. Okay, so in other words, this is going to be 7 centimeters, and this down here is going to be 4 centimeters. So to figure out this angle, this is the hypotenuse, this is the adjacent, so I'm going to be using cosine. So cosine of the angle is going to be equal to, well, what is it? SOHCAHTOA. So adjacent over hypotenuse. Well, the adjacent is 4, and the hypotenuse is 7. So the angle is going to be, if you put this into your calculator, 55.14 something, something, something. Okay? That's going to be the same as this angle here, which is the same as this angle here, which is going to be the same as these two angles up here, and of course over here. So now I can look at my, I'm just going to do this for 1, because I know that once I get, I'm just going to do one of these triangles, because once I get one of them, I can just double it to get the total. So let's go ahead and just make a triangle here so we can see. Let's go here. This value is given in the question. This is 500 newtons per coulomb. Then I've got my green component that I labelled earlier. This is EY2. And I've got my red component here that is EX2. And then my angle, which I had calculated using the dimensions, this is 55.14 something degrees. Okay, so now it's pretty easy. I'm not going to bother solving for the x because they cancel out. I don't need to know that. I do need to know the green one. So what is the green one? Well, this is opposite. So I'm going to be using sine. I'm going to say sine of the angle is soch. So this is opposite over hypotenuse. So the opposite here is the EY2. That's what I'm trying to find out. And the hypotenuse, of course, is the 500 newtons per coulomb. So if we plug that into our calculator, what do we get? We get 410.325 something. That's newtons per coulomb. And that's going to be in the upward direction or the northerly direction. Now, I need to double this. So in other words, let's just ring this off a little bit. Give me some space here. So I'm going to continue my EY net expression. My EY net expression is going to be 410.3 something newtons per coulomb plus the same. It's exactly the same, 410 something newtons per coulomb. So in other words, my solution to this question is, I'm just going to write this down here, is going to be 821 newtons per coulomb, and I'm just going to call it north. That's my solution.